Howdy folks, good evening. I've been watching some quantum physics videos, and I like to discuss about the double slit experiment, which is very known in the quantum mechanics. And I like to talk about, do quantum mechanical wave functions collapse if you observe in the two-slit experiment? Well, no. According to me, I think there might be a solution in what I'm going to present right now. And I presented, I think, a couple of months ago as well, but I like to explain it based on the double-slit experiment. And no, the wave function does not collapse. The wave function, if you observe a particle after the two slits, is altered. Well, I draw a little picture, and I will explain it to you. If you don't see me, it's not so important right now, as long as you see the picture, and I hope you understand. Well, the two slits experiment. Hope you can see it. A particle gun, whether it's photons or electrons or whatever kind of particle. The single slits, two slits, and the two-slit pattern. This is all known. But when you observe it, an eye here, I forgot the lashes, so sorry. Okay, or a detector, then all of a sudden the wave function which produces this, what in regular quantum mechanics is known, people think, they say the wave function collapses and becomes a classical particle. Well, I don't think so. What we have is the same setup, but the difference is an observer. And the thing is, what we seem to forget is that all objects are macroscopic objects, but which consist of particles that are strongly confined. So the wave functions of macroscopic objects, or the atoms, or the particles, the electrons, the protons, etc., of macroscopic objects, like you, like me, like this setup, are all macroscopic objects, but they contain a lot of very confined, energetically confined wave functions of atoms, electrons and protons and neutrons, etc. So it's very confined. What you can see is like macroscopic objects in this. Like they are strongly confined wave functions, and if they're more, they are more localized. I mean, you can see them in a scanning force microscope, in which the tip is localizing single atoms. And so it's very localized. But that means that if it's localized, it's more localized, so it behaves more macroscopic. And it behaves like this. It's a wave function, but it starts to wave, and then all of a sudden it dies out. But if you have single particles, there are less confined wave functions and less localized, the Heisenberg relationship. But then they also behave less macroscopic and more wavy, like this. And yes, in that case, it's logical that they behave like waves and show this pattern, the wavy pattern, wavy interference pattern with itself, because it passes here like a wave. And I forgot to draw the waves, but you know the classic the drawings, that the interference patterns, and they interfere and they deliver this pattern. But we seem to forget that macroscopic objects consist of more localized particles, which behave more like this, and thus more classically. So what we do is, if we measure the whole stuff, you use a macroscopic object with more localized wave functions interacting with a less confined wave function. And what happens, due to entanglement apparently, this wave function of the less confined wave function of the moving particle is all of a sudden altered by the macroscopic object, the wave function of the macroscopic object. Because what you do is you send a particle and you gain some information from it, and apparently by entangling the properties of the more confined, the more restricted particles in the macroscopic object, propagate their properties to the wavy function. So the wave function does not collapse, but it changes, it alters to more confined features. And so it becomes more classically, and that's why you find them after the two slits in either position, or this one, or this one. And but before that, before measuring, it behaves just like a wave function, a very wavy, self-interacting, self-interfering wave particle. But only at the moment that you are measuring it, then it becomes a part of the observed system, and thus more confined. And yeah, that's actually what so the wave function alteration by observation becomes more confined and thus behaves more classically. And thus you end up with this type of system. So you don't have a collapse, no, you change. You are, by observing, you are changing the wave function from a more spread out particle to a less spread out particle, a more localized particle. And well, that's when you end up with a more classical phenomenon that it's either that position or that position. I don't have the math about this. I'm not such a math things, but this is just a theory, an idea of how this idea could be explained, how the classical properties of particles return after observing. Due to entangling, you are actually exchanging information, like in the regular entanglement experiments. You are splitting one particle into two particles, identical particles, but going opposite sides. But after you measure it, then the properties of the other particle is known. Well, now you do actually the opposite. That you are bringing a macroscopic object in contact with a non-macroscopic object, a single particle, and then you alter the wave function apparently, and thus it becomes more classic in its behavior. Well, this is what I wanted to share. I don't have the math about this, and but I think this is an explanation. Okay, hope you enjoyed it, hope you understand it, and well, maybe I'm right, maybe I'm wrong, I don't know. Okay, thanks for watching, hasta la vista, see you next time, bye bye.